try to get the best equation that you'd get there, but kind of like that area that you have between that corner of the cube and then the outside of the sphere. So
okay. So all eight corners of the smaller volume would what? Touch the sphere, right? Just barely touch it?
Yeah.
So the bounding volume would be a over approximation to the size of the sphere, and the smaller box would be an under approximation, right?
Yeah.
And if we only had boxes, we didn't know how to calculate the volume of a sphere, but we knew how to calculate the volume of a cube or the volume of a rectangular box, a cuboid. We could basically try and fill up the inside of the sphere with little boxes because we know the length, width, height relationship, and we could kind of get the boxes smaller and smaller and smaller and put more and more and more in them to try to approach the limit of the sphere. Is that right?
That makes sense.
Okay. So when we think about the computer, we think that the computer can either do a lot of adding and a lot of subtracting, but it's not really good at doing triple integration. Okay? So what we need to do is we need to figure out an approximate method, some kind of numerical approach to doing these calculations. And the numerical approach that has been implemented on CAD systems now for probably approaching 20 years is using ray tracing to actually calculate volume, to calculate all kinds of properties done in the mesh properties. This little image that's on the screen, oh, Chris, thank you. You can relax. So
perfect.
You're off the hook. So this little example that's on the screen shows kind of a Boolean operation for building up this shape that's at the top. So the two cuboids at the bottom, the one on the right gets subtracted from the one on the left to make the image above it. And then what you do is you add the little cylinder to that middle object to get the object on the top, right? So that's how this problem has been built up. What they do with ray tracing is they basically fire a ray out through the object, and the ray is simply a line equation, and the line equation is really easy to calculate intersections on. And so if you look at the top image, you'll find that they fired a ray through that first U-shaped object or N-shaped object, and they indicated where it intersected and where it didn't intersect. So if you look, my mouse is not going to cooperate very well. If you look at that, whoa, slow down. If you look at that line right there, that little portion of the line is where the line intersected the solid object, and then a little further over to the right is where it intersected that same object again. The line just below that, so this line, whoops, right there, that line is the intersection of the same ray, the same exact ray, with the cylinder primitive. And then the line that is circled is the union of the two previous lines, of the two lines that are above it. And so you'll notice that first segment gets a little longer. And so what the computer is really good at is it's really good at firing rays out through space and figuring out when it goes into an object and when it exits an object. When it goes into an object, when it exits an object. And it's using those entry points and exit points to calculate a length or an amount of time that it's actually in the object. So that works good for one dimension, right? But the question is, how does it figure out the other two dimensions? Well, if you remember right, ray tracing basically took the screen and broke it up into little pixels and fired a ray through every pixel. And so if you want the other two dimensions, you have to answer the question, well, how big is the pixel? Because that is kind of the width and height, and the ray is the length of time, or the length that it's in there. So it can very quickly do all of this adding of pixel area representation by length of time it was in and out of the part. And by summing all of those together, it can get a very accurate volume calculation. Or if it's just doing area, it's counting how many times it's going in and how many times it's coming out. It's not worrying about the length. It's just counting how many times, and it takes that as a multiplier times the area, and so it can very quickly get the surface area calculation. Okay, does that make sense?
Yeah.
So is Kevin Spencer in the classroom?
Yeah, I'm here. Okay. Yeah, he's here.
So Kevin, if we do that process using the pixels on the screen and firing rays off through them, would it have any effect on how close I was zoomed into the model or how far away I was from the model? Does that question make sense? Would I get a more accurate answer if my model completely filled my screen, or whether it was a small dot in the middle of my screen?
Yes, it would.
So which is going to be better?
Zoomed in.
So as much filled the screen as possible, right?
Yes.
So that's exactly how they started doing this process when that was first being implemented. If you had your model and it was pretty small and it was in the center of your screen, it would give you one answer for the volume. If you zoomed in a little bit more, it would give you a different answer for the volume. If you zoomed in a little bit more, it gave you still a different answer for the volume. If you had it rotated on its side and you did it, it would be yet another answer.
Dr.
And so the very first... What's that?
The bell rang at BYU.
Oh, did it?
It did.
How long ago?
Just a minute ago.
A couple minutes ago?
Yeah,
Or just...
like 2 minutes ago.
Okay, so let me end by stating one thing. So instead of using the screen pixels, what it does is it puts a bounding box around the object. It's the smallest bounding box it can define, and it breaks up the bounding box space into little grid points based on some resolution. And the resolution is that slider bar. If you crank it way up to 99 or 100, then you get really small grid points on that box, and it'll calculate 1 billion rays ways almost instantly, and it'll calculate a accurate answer. Thank you, and we will see everybody after Thanksgiving, I guess.
Okay, thank you.
So please have a good Thanksgiving.